Well, let's move to larger scales. I'll take your mark. So first of all, I give credit to my collaborators, whom you can see in 3D. And I only have 20 minutes. I tried to ask for an hour talk from my friend Tole, but he didn't give it to me. So I can only answer, really focus on one important scientific question. And that question is, are gods kind to us? So let's first of all think what we know about star formation. So what we I think learned in the last 5 or so years is that the star formation correlates very well with molecular gas at low redshift and high redshift. We just know from observations. And we also have a very simple physical reason, as Mark, Adam, and Chris explained to us. This is simply from the fact that dust, cosmic dust, that is important both for cooling the gas and for turning into molecules. So it's the same basic processes that lead to cold and molecular gas. So let's now think about how we think about star formation. This is an equation that every simulation presented in this conference and which will be presented in the rest of this week actually used in one way or the other, or maybe using something for proxy for this H2. And this again, time scale may depend on density or on something else. So what I'm actually going to claim that this equation is wrong. And not only it's wrong, it's even conceptually meaningless. So I'm giving here a pop quiz. So 10 points. Who can explain me why it is wrong? No one wants brave enough to? No? Huh? Okay. But the reason why it's wrong is because the density is actually defined on a spatial scale. The density is not defined without a scale. Everyone who works on large scale structure knows that. That, of course, with gas, it's a little bit different because gas has mean free path. So on very small scale, density is unique property of gas. But scales we are dealing with in galaxy formation simulations are way larger than that. And so we have to define a scale in order to define the density. And so if I now think in terms of scales, what I should do is to take some spatial scale, then average all densities on this scale, and only those will be meaningfully defined. And then I can write the equation for which star formation rate is proportional to the density averaged over the scale, proportional to the density of molecular gas on this scale divided by depletion time scale. And this scale, this time scale will depend on spatial scale and density averaged on the scale, maybe on something else. But at least we have to think in terms of scale and density simultaneously. So in other words, we need to think in 2D. So I wish we could see in 3D, but at least in 2D. So we should think about scale and density, and this time scale for star formation. Basically, what we would like to do is to make some kind of contour plots. That is, of course, a cartoon. It's not a real contour plots. Might look very different, but we basically would like to do something like that, rather than just think about one axis of this plane. Okay, so what we know, what we can fill in this plane. Well, let's start with large scales. We know that at a local universe and scales of many hundreds and above, the depletion time scale of molecular hydrogen is density independent, actually. It's about 2 billion years. It's maybe 1.5, maybe it's 2.3, whatever, but it's in this range. And it's density independent, actually constant, which means that the star formation rate is actually a linear function of density. This thing is constant and just proportional. This is not an empirical fact, I'm not making this up. We go to large redshifts, at redshifts 1 and 2. We also have Koenig-Schmidt relations there. And this is, for example, plots from recent Genzel paper. And you can see the star formation rate does correlate with molecular gas pretty well. And the only little problem here is that the slope is not quite linear. It's like 1.17 or 1.27. So it's not 1.5, but it's also not 1. It's somewhere in between, which is kind of, for a theorist, of course, it wouldn't make any sense because the nature doesn't like those slopes. So turns out that this slope is not quite real. And this slope is not quite real because if you try to understand what this X factor, the conversion from observed CO luminosity and the real molecular gas surface density does, it turns out that X factor must increase at high surface densities for very simple physical reasons, right? Unless the metallicity is very low. So those are some of the examples of X-factor, modeling X-factor on galactic scales as a function of comb density or surface density. And unless you go to very low metallicities, like 10%, so it actually increases slightly, right, at high surface densities. It's a very modest effect, but if you put it in simulations, what you'll find that it explains entirely the slightly superlinear slope that Genzo and collaborators actually observe in high redshift galaxies. So in fact, these high redshift galaxies are consistent with having fully linear star formation law or constant depletion time scale. So what we can do now, go back to this two-dimensional plane and start filling it in. So on large scales, at higher and low redshifts, this depletion time scale is actually density independent. So this, my arrows mean, doesn't depend on density, and constant about 2 billion years, right, within a factor of 2. So let's now see what we can do on small scales. Well, and I don't know everything about star formation small scales, I'm not an expert, but we know that at very high densities, this claims by Lada, that the star formation time scale is again constant and density independent, but it's much shorter, about 20 million years. So it seems like, at very small scales it's density independent, at very large scales it's density independent. It's very tempting to fill in between, but of course Mark said something that makes the idea questionable. And in papers that drove all the simulation community in the last 5 years, Kramflex and Van claimed that star formation time scale is actually proportional to the free fall time scale, which is inversely proportional to the square root of density. So this is a constant efficiency per free fall time, Mark already mentioned. So if we now try to plot this back on this plane, you can take all the points. This is Apple. Yes, this is a conspiracy of Apple guys, right? So you can put these points. What I'm going to do is a very, very simple thing, a very silly one. I just take those observational points, right, from Mark's paper and just plot it here. Okay, this is giant molecular clouds which have a consumption time scale of about 500 million years on scales of tens of parsecs. And again, this is all cartoon version, right? The density is about hundreds. So we can do this infrared dark clouds. They have a shorter consumption time scale because the free fall time is shorter. They have effectively higher densities. Right? And of course, we can go to the HTN regions before somewhere there. And so what you notice is that Kramflex-Tan track goes like this in this plane. So it traces density, but it also traces a scale. So it can be a function of density, it can be a function of scale, it can be a function of both. Right? So these measurements don't actually tell you that it's uniquely a function of density. It only tells you that along this line, the star formation consumption time scale goes down, depletion time scale of molecular gas. So in fact, it's actually consistent with a very, very simple idea, right, in which the time scale for star formation is density independent, but it does depend on scale. Right? So when you average your densities on different scales, you get different depletion time scales. And of course, in this case, you have to have a threshold, because in this case, if the depletion time scale is 4 times shorter than, say, on large scales, of course, the galaxy still forms the stars at the same rate. You can still integrate this over the whole galaxy, get the same number. So it means that only 1/4 of the gas has to be in this region, molecular gas. So if you go to scales of tens of parsecs, with depletion time scale of 100 million years, only 5% of the gas, molecular gas, would have to participate in star formation. And again, the Lada measurements on parsec scales, only 1% of gas, molecular gas, can be star forming. So we have to have a threshold which is probably fuzzy because life doesn't have real thresholds. Right? And so if you now take and look how this time scale depends on how the consumption time scale, the time scale of star formation depends on spatial scale. So in very cartoon version, it looks like this. And so on larger scales, we know it's constant from Bigger and Genzo measurements. And then on small scales, it seems to be growing very crudely, right? In the cartoon version is linear. And this change in slopes may be due to whatever transition from two-dimensional to three-dimensional turbulence when we reach the scale height or something like that. But at least consistent with observational constraints that I'm aware of. So does it actually work? Right? So I'll show you some really preliminary results. Please don't take pictures. Right? Don't remember what you see. And in fact, if you close your eyes, it will be even better. So this is some of the simulations that I'm running right now of ionization. So those are big boxes which resolve everything down to 100 parsecs, very large petascale level simulations. And it seems like with this linear star formation law, I seem to be able to match luminosity functions, observed luminosity functions at redshift 5, 6, or 7. Again, the points are actually observational data that you've seen today several times in the morning, and 9 some my runs. So at redshift 7, I'm not quite matching them because even these big boxes, I don't have enough resolution, mass resolution to actually resolve this very first galaxies well. But at least at redshift 6 and 7, it seems to be able to match them. Right? So there's some kind of evidence that you can make, with those star formation models, you can make things look right at least at high redshift. So that's actually all I wanted to say. Right? So my main point, the one which I stand for, is that we have to think about star formation recipe, at least on large scales, as function of scale and density, right? Of these two parameters, not just one, because the density is actually not defined without the scale. And the data which I'm aware of are actually consistent with the linear density average star formation hypothesis, right? Which depends, so the time scale depends on spatial scale, but doesn't depend on density. And of course, there has to be a threshold. And in fact, there has to be scatter because it seems like observational scatter is more than it can be accounted for by simply uncertainties in X factors and H indicators, etc. So, and of course, in reality, gods are never kind. It would be too simple if that was exact a relationship at all scales without any scatter. So if this is true, if this hypothesis is true, then it actually makes lives of simulators much easier, because simulations have approximately constant resolution, at least the modern simulations as we run them, which means that we should be using a linear star formation prescription, not the 3/2 power law. This long consumption time scale on large scales eliminates the need for the early feedback. The problem with this 3/2 star formation model is that it makes way too many stars early on, and you have to do something special to suppress this early star formation of this early feedback types of model that Greg Stinson introduced recently. So if you don't have this 3/2 law, if you only have linear, then gas in fact remains as gas until redshifts around 3. So you have plenty of time to blow it out. Right? And then last but not least, the linear star formation recipe means that your simulations actually converge numerically. Right? At least in the limit when you don't have the feedback. Right? And so you can actually hope to get the converged answer which is independent of your resolution. So that's actually all I wanted to say.